Hey everyone, welcome to video 3.8. In this lesson, we're going to be learning about slope and equations of lines, and we're starting our notes here on page 215 together. We have two lesson goals. First of all, we're going to classify lines as parallel, perpendicular, or neither by comparing the slopes of those lines. And then we're going to classify lines as parallel, perpendicular, or neither again, but instead of comparing the slopes, we're going to compare the equations of the lines. All right, so to use slope as a criteria for determining parallel and perpendicular lines, we first of all need to review a little bit from Algebra 1 of what slope is. Slope is going to be, as we remember, the ratio of the change in the y-coordinate, we call that the rise, to the corresponding change in the x-coordinate, and we call that the run. So rise over run. Think about that list, rise, run in alphabetical order, okay? As you move from one point to another along the line, we're going to measure the rise over run to become the slope. The slope criteria outlines a method for how we prove the relationship between lines based on comparing their slopes. And we're going to, as we heard in our lesson goals, use those slopes to determine whether they're parallel, perpendicular, or they fall in neither of those categories. So here we have postulate 3.12, which is our slope criteria for parallel and perpendicular lines. First of all, the slopes of parallel lines, two distinct, meaning different from each other, and non-vertical lines are going to have the same slope if and only if they are parallel. Now remember, if and only if is a logic that we can take to flow in two directions. So once the non-vertical lines have the same slope, we can prove they're parallel. And if they're parallel, they also have the same slope. Slopes of perpendicular lines, the criteria there is that two, again, non-vertical lines are perpendicular. There's our if and only if again. This time, the product of their slopes is -1. Vertical and horizontal lines are considered perpendicular. Another thing you may want to add to your notes here on page 215 is that another way to determine whether lines are perpendicular, besides that the product of their slopes is -1, you can also think about that the slopes have a relationship to each other of being opposite reciprocals. Opposite meaning different in sign, and reciprocals meaning if I have A over B for the original slope, then the slope of my perpendicular, which I'll notate with that little subscript with our perpendicular symbol, will be the opposite sign over B over A, okay? So in example 1, we are to determine whether the lines AB and CD are parallel, perpendicular, or neither. And then we are given coordinate pairs for each of those 4 points. We're going to graph our line to verify our answer once we do our slope criteria on those combinations. Step 1 is going to be that we're finding the slope of the line. So first of all, remember we talked about rise over run. There's our rise, which is our change or our difference in our y coordinates, over our run, which is our difference in our x coordinates. And again, if we think about AB, a reminder that we had A was 3, 6, and B was -9, 2. So if it helps you to write your x1 comma y1 and x2 comma y2 underneath those points, then do so. But we can go ahead and notice that our y's are subtracted here. Y1 minus y2. Notice the formula has y2 minus y1. Did that on purpose because it does not matter which direction you put as which point you label as x1, y1. versus x2, y2. But what does matter, if you'll notice, is that you stack those points in this slope formula. So if you use y2 first, you use x2 first in the denominator. All right. So if we substitute in those points, we have technically reversed these subscripts. So 6 minus 2 is the difference in our y coordinates, and 3 minus -9, which becomes 4 over 12. Or if we simplify that, oops, wrong tool. If we simplify that, we get 1/3. Now, if we find the slope of CD, and again, you can go ahead and write those points down and put the subscripts underneath there for x1, y1, x2, y2 with those labels. The slope of CD is going to be 4 minus 3 over 5 minus 2, or also 1/3. Step 2 is going to be, now that I know those two slope numbers, determine the relationship. And this is pretty fast. The two lines have the same slope, and same slope lines are always parallel. Take a pause in the video and see if you can do this again with 4 new points. We're going to determine whether these two lines AB and CD are parallel, perpendicular, or neither, and then graph the line at the end to verify the numerical answers that you came up with for those slopes. In example 2, we have a different starting point. We're still comparing slopes of two lines at a time and determining whether they are parallel, perpendicular, or neither. But this time our starting point is not a list of points. It is instead a graph of two lines. So you can see though that we have 2 points on each line, so we can still calculate those slopes. If we take the slope of RS, our 2 points RS are -8, -3, and 6, 7. So we are going to go ahead and subtract 7 minus -3. Yes, I said 6, 7. Okay, everybody get over it. 7 minus -3, and then 6 for our x's minus -8. Notice we started over here with our right-hand point. We want to make sure we're subtracting in that same direction for our x coordinates as well. So that becomes 10 over 14, or simplifying that fraction, taking out the common factor of 2, we have 5 over 7. The slope of TU, on the other hand, is between the points -4, 6 and 0, 0. So we do some quick subtraction of our y's. 0 minus 6 and 0 minus -4 for the subtraction of our x coordinates. We end up with -6 over 4, or simplifying there and taking out the common factor of 2, -3 over 2. Let's analyze the relationship between those values. In this case, the numerical values of our slopes do not have the same slope, so we know that they are not parallel. And the product of those slopes is 5/7 times -3/2 is -15 over 14. That is not equal to what it should be equal to for perpendicular, which is -1. And so here we would say they are neither parallel nor perpendicular. For part B of example 2, we have two new lines graphed, EF and DG, and we're asked to find the slope of each of those lines. If we go ahead and find the difference of our y coordinates for E and F, we will take -1 minus 6, and that is going to be divided by 6 minus 3. Or if we go ahead and do that arithmetic, we get -7/3. And then our slope of DG is going to be between the points -2, -1, and 12, 5. So we'll take our difference of our y coordinates, 5 minus -1, all over 12 minus -2, which is 6 over 14, or if we simplify, there we get 3 over 7. So now we need to determine the relationship. So first we ask if they have the same slope. The two lines do not have the same slope, and so they are not parallel. We've ruled that out. But to determine whether the lines are perpendicular, we need to find the product of their slopes. If I take the first slope, -7/3, and I multiply it by that 3/7, we can see that opposite reciprocal relationship, and the product is -1. So because that product is -1, the lines are perpendicular. Take a pause on the video and see if you can calculate the slopes of these lines that are graphed and determine whether they are parallel, perpendicular, or neither. Our next learning goal from this lesson is to be able to analyze the equations of lines and determine whether they are parallel, perpendicular, or neither. So let's do a little bit of algebra review about the equation of a line that is non-vertical. First of all, we have our slope-intercept form of a linear equation, and this is our y equals mx plus b equation, where my m is the slope and my b is the y-intercept. Then a second form of the equation of a line is our point slope form, and that is y minus y1 is equal to m times x minus x1, where I'm taking a point and calling it x1, y1, and I'm taking the slope and substituting that in front of my x minus x1 in parentheses. Each of these forms is named for the values that you can read right off of the graph. So slope-intercept form, if you look at the equation of that, you know you can read off the slope and the intercept. Here's an example over on the right. We have y equals 3x plus 8. That linear coefficient on the x term is my slope, and my constant is my y-intercept. So in this case, m is 3 and b is 8. In our point slope form, that is what you can read right off of the equation, a point's coordinates and the slope. And if you'll notice in the example that we have over here, we have our y minus 5 equals -2 parentheses x minus x3. That value that's inside the parentheses with the x is my x coordinate of my point. The value that is next to my y is my y coordinate of the point. And I will just point out that we always have minus signs to start with. However, if my x1 or my y1 ends up being negative, in the form simplified, we would have plus signs there. Now let's talk about the equations of horizontal and vertical lines, and they are going to involve only one variable instead of a mix of x and y's. For the equation of a horizontal line, you're always going to have that to be in the form of y equals b, where b is the y-intercept of the line. So over here we have our horizontal line, and our y-intercept point is -3. So the equation of this line would be y equals -3. Go ahead and add that in your notes. And then the equation of a vertical line is going to be of the form x equals a, where a is going to be the x-intercept of the line. So in our vertical example over here, my x-intercept is at -2 on the x-axis. And so the equation of this line would be x equals -2. It's describing the coordinate for either x or y for every one of the points on that line. All of the points on this line y equals -3 have a y coordinate of -3. All of the points on this line x equals -2 have an x coordinate of -2. So when you're given the equations of two lines, you can compare the equations to determine the relationship between those lines. So here on page 218, we are given 5 different pairs of equations of lines. and we're asked to analyze whether these lines are parallel, perpendicular, or neither. We'll take them one at a time. In part A, our first pair of equations of lines, we can analyze what the slopes are coming out of those equations, which remember is going to be the coefficient in front of the x term. So in our first equation, our slope would be positive 3, and in our second equation, our slope would be negative 1/3. So the relationship there is that in part A, these two lines do not have the same slope, so the lines are not parallel. Different numbers can't have parallel lines. So determine whether the lines are perpendicular, we're going to find the product of those slopes. So if we take our 3 times our negative 1/3. You can remember that 3 as 3 over 1. And hopefully you recognize that opposite reciprocal relationship where the product is negative 1. And because it is, those two lines are perpendicular. Moving on to part B, we have the equation y equals 3 and x equals 1. As we analyze those two equations, we notice we see only one variable at a time in the equation. And so we know that they are horizontal for the first equation and vertical line for the second equation. And every vertical and horizontal line are always going to be perpendicular. In our third set of equations, letter C, we have y minus 5 equals negative 3/4 times parentheses x plus 2 and y equals negative 3/4 x plus 2. Again, one of these equations is in point slope form, one is in slope intercept form. So again, we want to find those slopes, which is going to be those coefficients in front of the x parenthesis or the coefficient of just the x term. In this particular case, our slopes are going to be equal. And so those lines will be parallel. In part D, we have two equations, y equals 2x plus 3 and y minus 1 equals 1/2. Find those slopes. In this case, they are 2 and 1/2. And what's the relationship? Those two lines do not again have the same slope, which disqualifies them from being parallel. But to determine whether they're perpendicular, we're going to find the product of those slopes. We had 2, which again we can call 2 over 1 if we wish, times 1/2. And when we multiply those two slopes together, we get a positive 1. The product of the slopes was not negative 1, so the two lines are not perpendicular. So we are saying that the two lines are neither parallel nor perpendicular. We end up with a neither outcome. And in our final pair of equations in part E, we have single variables in each of those equations. And so we know that an x equals equation and another x equals equation, these are both vertical lines, which are going to have an equal but also undefined slope. If you think about that vertical line and finding the slope between 2 points as rise over run, no matter what this rise distance is, the change in x on a vertical line is always going to be 0. That's a problem, dividing by 0, which is why we have an undefined slopes. So vertical lines are always parallel. The same thing, of course, is true with horizontal lines. Two horizontal lines are always going to be parallel as well. Take a pause on your video here and see if you can analyze each of these pair of lines and their slopes and determine whether they are parallel, perpendicular, or neither. All right, now that we know the relationship between parallel and perpendicular lines, we can try to apply these concepts into an application real world setting here. We have a design of a park that we're looking at, and we want to build a sidewalk that is going to connect the fountain here at point P on a perpendicular walkway to the existing sidewalk here, which we can think of being on a line that passes through points Q and R. So we're going to graph the line that represents that new sidewalk. Before we do that, we need to find the slope of the existing sidewalk or the line QR. And notice we can take our difference of our y's, 6 minus -2, divided by the difference in our x's, or 0 minus -6, -4 over 6, or if we simplify, -2 over 3. And because -2 over 3, its opposite reciprocal here would be 3/2 to give us a product of -1. The slope that's going to go through point P is going to be that 3/2 that we need. So if we graph that line and remember that 3/2 represents rise over run, we can start at point P and we can walk with a rise of 3 and then a run of 2, which puts us right there. So our point is here. Now, we know our sidewalk, though, needs to land back towards the original sidewalk. The new one that we're creating needs to go back towards the sidewalk from the fountain. So as we think about rise of 3 and run of 2, we can go up 3 and right 2, or we can also reverse both of those directions and go down 3 and left 2, and we will still be on that same trajectory. So this would be our new sidewalk right here. And those steps are written out for you there on page 219. I like to do my drawing right on the actual map of the park. So you can see, though, that's exactly what we just did. Move up 3 and then right 2. We can put another point there, but we can also go back the other direction and connect the points backwards. Take a pause on the video and see what you can do with this map of our metro lines. We need to create an equation in slope-intercept form that represents the E line, which is this light green line right over here. See if we can find the equation of that E line. Our last type of example is going to be actually writing equations of those parallel and perpendicular lines rather than just comparing them. So here in example 5 on page 220, we are writing an equation in slope-intercept form. So remind yourself what that means. Y equals mx plus b for the line that is parallel to y equals -3/4 x plus 3 and goes through the point -3, 6. Notice we have a slope that we can read off, and we have a point. So in slope-intercept form, the work we would want to do is to go ahead and find a parallel slope, and the slope of that -3/4 x, pulling off that coefficient of x, is -3/4. So parallel slope is going to have that same value. So you'll notice that that's staying in our m spot in y equals mx plus b. And then the point that we are going through was -3/6. So we can plug that in for the x and the y value. And then we need to do a little bit of arithmetic. -3/4 times -3 is giving us a +9/4, which then we need to subtract 9/4 from each side, keeping in mind that our 6 here is 24/4. So I have 24 minus 9/4, or 15/4, which is my b value. So my equation in slope-intercept form is going to be y equals -3/4, same slope, but our new b value, 15/4. For our last check, take a pause on the video and see if this time you can write an equation in slope-intercept form parallel to 1/2 x plus 5/2 and containing through the point 3/2, 1. Okay, everyone, this is the part of the video where you really want to check back on the answers to those checks that were assigned to you as you were watching. Okay, back to our first check, which started us off on page 215. In this case, we get neither for an answer. The work that you would want to do to support a question like this would be first to find the slope of segment AB or line AB, and that would be, notice how I'm labeling that with a little subscript, 13 minus 0 all over 14 minus -11. Between those 2 points, we can simplify that to 13 over 25 would be the slope of AB. Compare that to the slope of CD, and our change in y is going to be 7 minus -5 all over -3 minus -4. And so we have 12 over 1, and those two slopes are not equal, so we know they are not parallel. But if we take their product, 13/25 times 12 over 1, I'm not sure what that is, but it's certainly not -1. So we end up with neither. Hopefully you could see that verified visually as well. Those lines clearly are not parallel because they're intersecting, and does not appear that they intersect at a 90-degree angle either. Okay, hopefully your next check there on page 216 was a pretty quick answer, but let's go ahead and talk about the math that supports this answer of perpendicular. Going over to our graph, the points that we would have, the coordinates that we would be coming up with are like so. And so if we just take our slope of AB as we just did in our last check here, notice that would be 1 minus 1 all over 8 minus -2, otherwise known as 0 divided by 10, which is 0. So the slope of our line AB is nothing. Now, the slope of 0, the opposite of 0, right, is still 0. And the reciprocal of 0 is where we start to have a little bit of a problem. Look at the arithmetic that results when we find the slope for CD. We get 5 minus -2 all over 3 minus 3. Numerator of 7, not a problem. But denominator of 0, that is a problem because that is an undefined value, okay? These two numbers, when they result from your arithmetic, should bring to mind that those are perpendicular slopes. 0 would be our horizontal slope, and undefined would be our vertical line's slope, which is not really possible to give a number to. So keep that in mind. For our check for example 3, you can see the answers here. Just analyzing the slopes, we can say perpendicular because 3 times negative 1/3, thinking of that as 3 over 1, does equal negative 1. Obviously, those two numbers are not equal, so not parallel for sure. If I target the slope in the pair of lines in B, we have 9/7 and 9/7, easily equal, and so parallel lines. And then I have two one variable at a time equations, which both happen to be both vertical lines, and so we have parallel there again. All right, the answer we should come up with for the check, for example, 4 here on page 220 is going to be 8x minus 67. Let's see how we arrived at that. First of all, the E line, remember, needs to run parallel to our A line, and our A line has the equation y equals 8x plus 11. So of that equation, we're going to target that slope of 8, and we know that we're dealing with our new equation also having a slope of 8. And we know that we're going through the point that we can see on the graph here, being at point on the E line 9, 5. So I can start with a point slope equation. Y minus y1 equals m parentheses x minus x1, writing down the formula first, filling in what I know. I know my y1 is 5, my m is 8, and my x1 is 9. If we distribute, because we do need slope intercept, so y equals mx plus b, we can distribute that 8 through that parenthesis, and we get our next row looks like 8x minus 72, which then we needed to add 5 to both sides. So y equals the 8x minus 67. Look at that. Okay. Hopefully that makes sense to you because if we were to walk along this line E or E line on the metro, remembering where our y axis is, hopefully you can think about those two lines intersecting way off of that grid. And that's why we are all the way down there at that y-intercept. And for our final check on example 5 on page 220, we're looking to write an equation in slope-intercept form. So, whoops, wrong tool. If we remind ourselves that, of course, we're ending with y equals mx plus b again, but notice what we're starting with is running parallel. So we have our slope of 1/2 and going through a point. If we have both values for the point, we can think of that as x1, y1 for our point slope, or we can go right straight to slope-intercept form and substitute in x of 3/2 next to our slope of 1/2 and our y value of 1. So we have 1 equals multiplying numerator times numerator over denominator times denominator, and then subtracting that fraction from both sides. We get our b value is 1/4. So we have our 1/2 original slope and our new b value in our equation. All right, we'll see you in the practice.